All right, welcome to topic 7. We are introducing this big word, volume. We're going to talk about prisms and cylinders, mainly because, like I said before, cylinders kind of are just are prisms with circular bases. And so we're going to look at this idea of volume and what volume is. Okay, so we talked about surface area and what that is. That's the space on the outside. Like if I was going to paint a building, I'd be talking about the surface area. Okay, it's just a bunch of 2D faces that I'm adding up. Volume's a little bit different, and I'm sure you've experienced it before, but it's how much space is inside of an object. Okay, so if you look at this room, all right, surface area is the floor, the walls, and the ceiling, right? If you were going to paint that, and then volume would be like if I was going to fill this room up with water, okay, that would be volume. How much water could I fill in this three-dimensional space? So this is going to be all about three dimensions. So I like to call volume space inside of a 3D object. Whatever it might be. Cereal box, how much cereal can I fit inside that box? As opposed to how much cardboard does it take to make that box? That's surface area. Okay, so there's lots of different objects there, objects to think about. How much Coke is inside that can versus how much aluminum makes up that can. Surface area versus volume. Okay, so we're thinking about filling up stuff. So if you think about it before, I told you area is like, let's say I was talking about square inches, right? Area is in terms of square inches. How many little 1x1, cute little 1x1 squares can I fit inside of an object, right? You got like this, even if you had kind of a weird shaped object, it'd be, how much space is inside of that thing? You'd be counting squares here. Well, now we have three dimensions, so we are no longer talking about squares. We're actually talking about how many 1x1x1 cubes, and this is going to test my 3D drawing skills. It's how many cubes can I fit inside of something, right? I think of like little sugar cubes that you feed a horse or something like that. How many of those could I fit inside of a can or a glass or this room even, all right? Or if we're talking about something bigger, if we're talking about feet, okay, how many 1x1x1 foot cubes could I fit inside here? That'd probably be a better estimate of what's going on in here. Okay, so we're no longer going to be talking about centimeters squared or inches squared or even miles squared. We're going to be talking about inches cubed. How many cubes can I fit inside of something, or how many feet cubed can I fit inside of something? So it's kind of a much larger measurement because we're having three dimensions now. We're getting a depth involved here. So I'm going to skip over these. How much, like, let's say I just want to look at them for a second. Like, how could you tell how much stuff you could fit inside of here? Let's say you're trying to pack something to send, you sold something on eBay and you're trying to pack it in a box and you're trying to figure out which box will this fill in or which one has more space inside of it. That's what we're talking about with this idea of volume. How much space is inside of something? Do I want this can of something or this can of something? Which is going to have more based on its dimensions? And I think we're going to skip over an activity that's a good one for that. So let's just talk about a volume of a prism. Okay. We've talked about surface area being just the adding up of the faces, and we have a bunch of rectangles here, and it says if B big, notice it's big B. We're using little b before for the base, the length of the base. This is big B, is the area. Put a big star here. It's the area of the base of a right rectangular prism. And H is the height of the solid. How tall is it? Okay. So then our formula becomes, it's very simple. It's simply, it was little b times h before. This is big B times h. So it's the area of the base times the height of the shape of the solid. Okay, so if you look over here, there's actually, with a rectangular prism, you could call this the base and this the height if you wanted to. And it wouldn't actually matter because you could call this, so let's say this, you can see the bottom of it. You could call this the big base, this big B, and then this would be the height. So it kind of depends on which way. It doesn't matter which way you do it. It doesn't matter exactly which base you pick, as long as if you're talking about a prism, you're talking about the faces that are parallel. But with the rectangular prism, it doesn't actually really matter. All right. So I'm going to skip over this activity, drop down all the way to the beginning here, all the way to the bottom. All right. Again, we have if big B is the area of the base. All right. Well, we're talking about a cylinder, so that's always going to be a circle. So that's always going to be a circle for a cylinder. And h is the height. Okay. So here's our height. Here's our base, if you want to think of it like that. This is our big B. This is our space inside here. Then our area is going to be, we could say A equals big B times H, again, just like our prism formula, but we know the area of the base of every cylinder. Since it's got to be a circle, it's just going to be, I don't know why I'm putting A here. It should be V for volume. Did I do that on the last slide? If I did, fix it. All right. We know that the area of a circle is pi r squared, so we're just going to do pi r squared h. Where this is really just big B, we're replacing big B with our pi r squared that we know is. Okay? All right, let's do a few examples. I hit you with the formula pretty fast here, but you may have seen it before. Let's do a couple examples here, and then you can work on your own. All right, obviously we have a cylinder in letter A. So we've got our volume equal to, okay, the area of the base, which is pi r squared, so pi times 8 squared times our height of 7. Type all of that in. I guess if you type this in, I got an answer in between 448 pi, but you get approximately, and again, double check my work, if I round to the nearest tenth, 1407, and that is kilometers cubed, or that's a mass. That is 1 kilometer by 1 kilometer by 1. Think about it as in terms of a mile. That is a huge space. I don't know what kind of cylinder this is, but it's taking up like an entire, just a massive amount of space going way up in the sky, a mile up in the sky, basically, if you're sitting it down on Earth. So maybe not terribly realistic, but that's how you make that calculation at least. Okay, let's talk about this next one. Let's actually jump down to C. We'll do maybe what I think is the easiest one of these three. So C is obviously, it's going to be a prism, but it's about finding the base of the prism. Well, the only two faces that are parallel are these triangles right here. All right, so when I do volume and I do big B times H, my big B is going to be of that triangle. So I need the area of a triangle, which we've done before. It's 1/2 the little b times h, okay? So the little b of these triangles that are the same, the base is, you could choose whatever you want, okay? You could choose this side or this side. I would not choose like the hypotenuse. This is 3, and that's 4. So it really doesn't matter what order you call it in, but that's 3 and 4, 1/2, 3 times 4. That is the base. That's the big B here. And then I got to multiply it times h. And so the height, if I turn this thing and set it on its base, let's say I set it on this, right? How tall would this thing be? It'd be this length here, which is actually the same as that length over there. It is a 3, and that is the height of my prism there. Plug all that in, you get a volume approximately equal to the nearest tenth of, I think I got 18 feet. I could just, yeah, this isn't terribly hard. 1/2 of 4 is 2. 2 times 3 is 6. 6 times 3 is 18. So it's exactly 18 feet cubed. All right, so if you want a general sense of what that is, that's look at the floor, and you got to go 1 foot up, and that's what a 1 foot cube looks like. All right, let's just go on to D. D is going to be another cylinder. All right, our base is going to be the only two sides that are parallel, that are congruent and parallel. These look like they're congruent. This bottom one and this top guy look like they are too as well, but they're not congruent. All right, I should probably throw that in there. These trapezoids right here are really going to be our base. All right. So if we start calculating our big B, all right, we are going to use the trapezoid formula, which is base 1 plus base 2. So that's 3 plus this distance right here is the same distance over there. 3 plus 8 divided by 2 times our height. So the height is right here. That's 4.3. And that right there is big B. Now we got to multiply it by the height of this thing. The height is got to be, well, it's, if I set it on its base here, this trapezoid right here, it's going to be this tall or that tall over there. That is 4. And that's our height here. And I'm getting a volume of approximately 94.4 meters cubed. And that is, again, massive because a meter is almost like a yard. So these are just like giant, if you want to think of it as like one of those, the boxes that you do box jumps on, or the Chromebook cart up here. It's actually bigger than this storage thing for the Chromebook cart. That is what 1 meter cubed is, and that's 94 of them. So we might be able to fit them in here. It'd be pretty close. It might be a good accurate representation of how much space is in this classroom. But anyway, last guy right here. We've got so if you look at our base, it's going to be this 1, 2, 3, 4, 5, 6. It's going to be this hexagon, which we have found before. So this gets a little bit more complicated. I'm going to kind of do it. So our big B is going to be the area of our hexagon. If you remember our hexagons or our regular polygons, they're regular, all the sides are the same. We have to find the area of that triangle and multiply it by the number of triangles that are in that thing, and there's going to be 6. So the area of that triangle, 1/2. Base, let's see, our base is actually 4 here because it's 4 up here. Okay, so our base is 4 times our height, which is 3.5, times, okay, so that's the area of one triangle, and there's 6 of them, so times 6. Whew. And that's just the area of the base, right? That's the area of the base. We need to actually then multiply it by the height, right? This is right here is, yikes, I'm not sure what that was. There we go. That is big B. We need to multiply it by the height, which is 3 feet. And I'm getting some, I think exactly 126 feet cubed. All right, there's 4 examples for you. If you flip over, you've got the next 4 to do. They chunk it out and give you, hey, you have to find the area of the base, and then you go find the volume. But again, make sure that you know which is our base and which is the height when you're identifying that. So good luck there, and then you have some Khan Academy to work on after that.